For numerical integration, we have two exercise tasks. So the task one was to show that special purpose integration grids typically yield better accuracy than regular rectangular grids, even though the rectangular grids are easier to calculate. Particularly in the context of chemistry, that's highly relevant. So you have some example code that calculates most of what you need for the density. In particular, the QM calculations are already written. So that's why the task is divided in 3 steps. So the first step reads get the molecule and the density matrix from a QM calculation using get N2 molecule. That's the first function over here, which returns two things. It returns one molecule and one density matrix object that we later on need for the get density function. So I write the variable for a molecule and for a density matrix shall be get N2 molecule. And if I do that, I can just run it directly, and now I have these two variables. The next step was to get the molecular integration grid with this function get molecular grid, which is already implemented. And what it returns is grid positions and grid weights. So the weights are the alpha coefficients in our typical numerical integration scheme, and the coordinates are the points at which we'd like to integrate our 3D function. So I'll just add another line, and let's call this special purpose grid positions and special purpose grid weights. And the result of that is whatever comes from get molecular grid. So now the third step was integrate the total electron density with that molecular grid. And this is supposed to be close to the total number of electrons in the nitrogen dimer, as the task states. So let's calculate precisely this. So I write print special purpose grid, and I would like to get this grid value. Let's maybe make this a new variable. So special purpose integral shall be this get density function. And what we have is in this get density requires a mole object, a molecule object, density matrix, and integration positions. And we have those ingredients. So we have get density as the function. The first argument should be the mole. That's exactly what we have from the get N2 molecule. The density matrix from the same function. And now we only need the positions. So that's this variable with the positions. This allows us to evaluate the electron density, so electrons per volume, at the positions of this grid. But now to get the integral, as in most integration schemes, we need the product with the individual grid weights. So we multiply this with the grid weights, and then we sum this up. So I put brackets around it, and there's a nice function in NumPy that you can just call dot sum, and it's going to integrate or sum up all vector components. This multiplication over here is element-wise, so for every position there's going to be the appropriate weight multiplied with it. So if we now print the special purpose integral variable and just run it, then it's unhappy about one object. Yes, the molecular grid still requires to specify the molecule. And now if we do that, what we get is something which is 13.59, and that's very close to 14, which is the total number of electrons in the nitrogen dimer. So the special purpose grid served its purpose and worked beautifully, but now we wanted to look at the regular grid, the rectangular grid. And for this we need to complete this one function. So there is a stub, but it's not all the code that is already present. So what we have here is the first entry for n, where we need to specify the proper grid points in order to make this about as relevant as possible, so as matching as possible. And we do that by first looking at how long our actual integral is. So we have the vector of grid positions, for example, we can ask we can ask Python how long is it, and it's 10,360 elements long. And the task was set this n to match the grid point count of the molecular grid most closely. So if we take the third root of that, because it's a three-dimensional grid, then we get 21.8. So it can either be 21 or 22, which is closest. And you can actually calculate that. We can say 21 to the third power and 22 to the third power. And then we see that actually the 22 is closer in this, off by just 200 points. So for a fair comparison, we want to have roughly the same number of points between the two grids. And that's the reason why we have to set n to 22 in our case. Now we have the grid spacing. This is already defined over here. We know the grid positions in x, y, and z, but we need to generate all those different points. And you can see from the return signature that we're going to return two vectors, namely one is positions and the other one is weights. And it's the same concept as for the function for molecular grids, where we have the positions and the weights. So let's create two new arrays, one called positions, which shall be an empty list, and then one called weights, which again shall be an empty list. Now, the simplest way of generating the full grid, not necessarily the computationally most efficient, but the most readable way would be to say for x in grid, so just three nested loops, for y in grid, for z in grid, loops over all possible pairs of the individual grid coordinates. And now we can do positions append the combination of x, y, and z. So this way we get a tuple containing x, y, and z into this list positions over here. Now we also need the proper weights. And now keep in mind that the weights come with a unit. So we need to give the proper integration units for electrons over angstroms cubed, meaning if you have some function, say f on x, and you integrate it over x, then the units of the integral is the units of f times the unit of x, because you get the area under the function, so this way you get the product of the two units. And this means that our integration weights are not the total count, how many entries there are, because that would just give the average electron density. What we want is its integral, so the weight must be the volume that relates to the total electron, to this particular data point on the grid. And the volume of the grid is just the distance between the grid points, so say grid 1 minus grid 0, or any other grid point, to the third power, because the grid is an angstrom, and this grid over here, this distance is the grid spacing, so every data point represents precisely this volume. So now with these weights, we build up the whole function. So I have to rerun this section such that the changes are reflected. Now we can write an analog for the regular grid point. So let's say regular grid positions and regular grid weights are the result of get regular grid, which does not depend on the molecule because there is no molecule, no relative position to the molecule. And now we can say we integrate that, so it's the same logic as here. We say regular grid integral shall be the density at those points, so get density with the molecule, the density matrix at regular grid positions times the weights, so times this regular grid weights. And again, in the result, we would like to sum this, so we write dot sum, and now can give regular grid and say this is regular grid integral. So if we run this, then now we get one number which is nearly 14, as we've seen before, and one number which is close to 10.5. And since the task asked for the absolute difference, we finally calculate exactly this. So it's the special purpose integral minus the regular grid integral in absolute terms. So the answer is 3.511. Now for task 2. In task 2, the question was that numerical integration sometimes can be done by calculating random data points. We've seen Monte Carlo as one of the classes that does precisely this for integration. And in what we are doing now for the n-dimensional sphere, we have a very similar concept. So let's write the function n sphere volume to do exactly this. So we're going to ask for a dimension and 4 tries, because in the task we have 2 sphere and 100 random points as a reference, so we can test our code. So we would like to have this more flexible. So we ask for dimension and tries, and the first thing we need to do is we need to get random data points. But the task requires us to initialize these random points with a seed such that we all get the same pseudo-random data points. So I'll just add this to our code. Finally, we can now get our random points, and I will just call this sample points, and it shall be just this random call that is already in the task. So this means it gets points between -1 and 1, and it means it gets, for every try, it gets 1 data point for every dimension. Now the definition of a unit sphere is that the distance to the origin is less than 1. So we can calculate all these lengths by using, for example, the linear algebra norm function, and for this we need to give a vector, so that would be the sample points, and we need to specify along which axis we'd like to calculate that. In this case it's 1. You can also write a nested for loop that goes over every try and calculates the square root of the squared values. Either way would be equivalent, because now we have a vector of all the length. And as shown in the lecture, we have the opportunity to write length.where is numpy where length is smaller than 1. Now this returns a selector of that array where the entry is smaller than 1, and we can say we would like to have the 0 dimension for that, because that's the way how NumPy works. It's also explained in the lecture. So now we get the list, and this is just a long list of indices where length is small enough, so smaller than 1. So now what we can do is we can ask for its length. So this means how many of those random points are closer to the origin than 1, so are within the unit sphere. If we divide this by the total number of tries, we now have the success ratio, so how many random points are within the sphere as compared to all those that we have ever tried. Now we need to normalize this by the volume of our random sample point distribution. The idea was to have a simpler to calculate volume as a reference, for which you then do this random sampling. And this is easy to calculate because these are random points from -1 to 1, so on a sphere, on the hypercube of length 2, and it has the volume of side length 2 to the power of the dimensions. So this way we have now our resulting volume. We return that, and now we can just test it with the numbers given in the task. So we say with 2 dimensions and 100 random data points, we get 3.04, which is the answer given in the task. So now we can ask for the 5 sphere and 100, and then 4 zeros, data points, and the answer is 5.271904.